Chronic consumption of high-fat diets exerts a profound and often damaging effect on cellular health, not only through direct caloric excess, but by disrupting the body's internal maintenance systems, particularly autophagy. While cells are equipped with mechanisms to process and adapt to short-term nutritional changes, a prolonged intake of high-fat, energy-dense foods can suppress autophagic activity in multiple tissues, including the liver, adipose tissue, pancreas, and muscle. This suppression has far-reaching consequences, accelerating fat accumulation, metabolic dysfunction, and the progression of obesity-related diseases. Autophagy plays a critical role in cellular housekeeping. It identifies and clears damaged organelles, misfolded proteins, and toxic byproducts, especially under stress conditions like nutrient scarcity. In the context of a high-fat diet, however, cells are continuously flooded with excess fatty acids, which alters cellular signaling and disrupts the finely tuned balance that governs autophagy. Specifically, nutrient-sensing pathways such as mTOR, mechanistic target of rapamycin, become chronically activated by the abundance of dietary fat and insulin, sending inhibitory signals that shut down autophagic processes. This means that just when the cell most needs its internal cleanup system to manage lipid overload and oxidative stress, it is functionally paralyzed. The result is a dangerous accumulation of biological waste. Mitochondria, overwhelmed by fat oxidation and unable to detoxify fully, become dysfunctional and leaky, releasing reactive oxygen species that further damage surrounding cellular components. Lipid droplets build up inside cells without being adequately broken down, a process that would normally be handled by lipophagy, a form of autophagy specific to fat metabolism. As autophagic efficiency declines, cells lose their flexibility, their ability to adapt to energy fluctuations, and their resilience to stress. In the liver, this suppression contributes directly to the development of non-alcoholic fatty liver disease, NEFLD, as hepatocytes are unable to dispose of excess lipids. In muscle, impaired autophagy can reduce insulin sensitivity and increase intramyocellular fat, weakening metabolic control and contributing to fatigue. In the pancreas, it interferes with the normal function of insulin-secreting beta cells, impairing their ability to regulate blood glucose. Each of these failures reinforces the next, creating a self-perpetuating cycle of metabolic decline. Despite these risks, the picture is not entirely bleak. The suppression of autophagy by a high-fat diet is not irreversible. Animal studies and early human trials have shown that lifestyle interventions, particularly those that create intermittent energy deficits, can reactivate autophagic pathways even after prolonged exposure to unhealthy diets. Fasting, time-restricted feeding, and aerobic exercise help reset nutrient-sensing systems, suppress mTOR activity, and increase the expression of key autophagy genes. This reactivation can restore mitochondrial function, reduce intracellular fat buildup, and improve systemic insulin sensitivity. Moreover, certain nutrients and plant-derived compounds may counteract the autophagy-blocking effects of high-fat diets. Polyphenol like quercetin, EGCG, from green tea, and resveratrol have shown promise in stimulating autophagic flux, reducing lipid toxicity, and enhancing cellular stress resistance. Their use alongside diet modification could offer additional support in reversing high-fat diet-induced damage. Yet, a warning must be issued. While it may be tempting to rely on supplements or occasional fasting to offset the effects of a high-fat lifestyle, such strategies cannot fully substitute for consistent, foundational changes in diet quality. Chronic exposure to excess dietary fat, particularly saturated and trans fats, creates deep cellular dysfunction that compounds over time. If unaddressed, it can overwhelm even the most robust compensatory mechanisms, leading to permanent damage in tissues like the liver and pancreas. The suppression of autophagy under these conditions is not simply a side effect, it is a core mechanism of disease progression. In conclusion, the link between high-fat diets and autophagy suppression underscores a deeper truth about metabolic health. The body's resilience depends not just on what it consumes, but on its ability to recover, clean up, and adapt. When autophagy is blocked, that resilience erodes, and the consequences ripple through every system. But the good news is that autophagy is highly responsive to positive change. Even after sustained periods of poor dietary habits, the body retains an incredible capacity to recover, if given the right conditions. Supporting autophagy through dietary moderation, intermittent energy restriction and regular physical activity may prove to be one of the most effective strategies for restoring metabolic balance and preventing the long-term complications of a high-fat lifestyle.